Hi everyone, welcome to Introduction to Data Science. My name is John Kim, and we're going to walk through this course together. So why data science? Well, number one, we're in Seattle. And as we know, Seattle is the heart of the cloud, which means there's going to be a ton of data that our clients need help with. Number two, AI is the future. Data science is an enabler of that, and we're going to help get the firm to that future and be a leader in the space. Number three, the market is huge. $12 billion were spent on AI in 2017. That's going to grow to $57 billion by 2021. Several research reports indicate there are a huge number of customers looking to enter into the AI space as well, which means that's a lot of cheddar. But most importantly, our clients need the help.
Here's a fun fact to put things in perspective. Around 95% of all the data in the world has been generated in just these last few years. And that flood is going to get worse. By 2025, we will be generating 25 times more data a day. That is quite literally an incomprehensible amount of information. But that's where data science comes to the rescue. Using a combination of big data practices, machine learning, and old-fashioned analysis, we can help clients make sense of this big, hairy, and audacious data world. And thanks to the breadth and depth of our capabilities, we are well positioned to do just that. All of our core capabilities will play a critical role in the coming years in both delivering new value to clients and helping unify in our journey to regional leadership in AI solutions and services. So with that as our motivation, let's start learning some data science.
What really is data science? The definition, it is the interdisciplinary field dedicated to extracting insights from data. Now there are three parts to delivering data science solutions. One is having business acumen, two, statistics, and three, coding. And the combination of those three domains is where data science adds value. Now you might say, okay, this is a pretty simple concept. What is with all the hype? Well, the hype is this, artificial intelligence. We've all heard it in the news, we've all read articles on it, but this is the reason why it's become so big, AlphaGo. AlphaGo was a machine learning algorithm designed by some deep learning researchers that actually beat a human being at the game of Go, which everybody predicted was impossible. Other things that we're seeing in the market, Amazon Go, all your home connected devices, self-driving cars, and of course, facial recognition, all powered by AI. Now, where does data science come into all that? If you look at artificial intelligence as a domain, a huge contributor to that is machine learning. Within machine learning, you have deep learning. And data science has actually contributed to much of that progress because that's what we do. We use data to inform algorithms who then predict the future. So with that has come this huge boom in artificial intelligence adoption across industry. Here's just a sneak peek of what's to come. Let's dive a little deeper. We've talked about the why, we've talked about the what. Let's talk about how we data scientists add value to industry. We're going to lean on this video to give us a quick crash course. They're going to introduce us to lots of great applications. And once you're done, we'll come back and talk about what this means for Unify.
Hey, and welcome to our brand new series in which we're going to get you up to speed on artificial intelligence for marketing and growth. Predictive analytics is a form of data mining that uses machine learning and statistical modeling to predict the future, based on historical data. Applications in action today are all around us already. For example, banks have been using predictive modeling to approve or decline your credit cards and personal loans. But it's not only that, it's also used for weather forecasting, recommendation engines, spam filtering, and fraud detection. So why should marketeers care? Imagine if you could not only determine whether a lead is a good fit for your product, but also which are the most promising. This will allow you to focus your team efforts on leads with the highest ROI. And this will also imply growing from quantity of metrics to quality of metrics, which leads to focus more time on. A financial services provider can use thousands of data points created by your online behavior to decide which credit card to offer you and when. A fashion retailer, based on the jacket you just bought, can use your data to decide which shoes to recommend as your next purchase, based on historical behavior that other customers have had in the past. But the implications are much bigger than that. Retailers can predict demand and therefore make sure they have the right level of stock for each of their products. Every time we type a search query into Google, Facebook, or Amazon, we're feeding data into the machine, growing ever more intelligent. To leverage the potential of artificial intelligence and predictive analytics, there are 4 elements that organizations need to put in place. First of all, you need to ask the right questions. Which questions am I trying to ask with my predictive analytics? Which metrics am I trying to forecast? Which future behavior am I trying to predict? You need a sound hypothesis to actually test. The second one is having the right data. We've come a long way in terms of data availability. It's been said that 90% of all of the world's data has been generated in the last 2 years. But we still do need complete and clean data sets to arrive at plausible conclusions. It's important for you to figure out what data is available to you and whether it will be sufficient to answer your questions convincingly. Third of all, we need the right technology, whether or not a particular software is right for the problem you're trying to solve. And finally, it's the right people. Without the right people, it's impossible to pose the right questions. Let's look at staff retention at IBM. IBM is using predictive analytics to retain its employees and come up with possible solutions to forego higher turnover. By uploading a structured data file, Watson can spot the common factors in employee dissatisfaction. This then feeds into a quality score for each employee based on their predicted likelihood of leaving IBM. This is what we call people analytics. Next, let's look at supply chain optimization at Walmart. Walmart takes data instantaneously from its system and incorporates it within its forecast to assess which products are likely to go out of stock and which have actually underperformed. Combined with behavioral data from its customers online, this provides a huge amount of data points to help Walmart prepare for increased or decreased product demand. Forecasting this allows Walmart to personalize its online presence, targeting customers with specific products based on their predicted likelihood of making a purchase.
All right, that was a lot to cover, but that's kind of the point. Data science is adding value in every corner of industry across a variety of different applications: banking, supply chain, e-commerce, fashion, and even HR. And the rate of adoption is just going to increase from here for every industry. To make it a little more concrete, let's look at an example that we're all familiar with: insurance.
You mean I'll be charged fairly? That's a novel concept. Today's customers demand more value for their money, not necessarily at the lowest cost, but at the right cost. Some companies have business models that are difficult to change and adjust to these expectations. So machine learning may come to the rescue. Take an auto insurance customer today. His premium is calculated on a fixed amount for the whole year, averaging out risks for him and his auto for that whole year. In reality, however, risks change in real time. When his car is parked in a garage, chances of an accident or a catastrophe is small. When he's driving on a crowded 2-lane highway, his risk is high. So what's the big deal? Insurance companies average out the actual risk. If the company estimates an average that's high, then it's making more money than it should. If it estimates an average risk that's low, then it's losing more money and may shut down soon. The ideal situation is when the premium changes with the risk, with some buffer built in for operations and profitability. So the closer the premium follows the risk curve, the better it is for the customer and for the company. With today's technology, this is possible to achieve. A simple GPS unit on a car can track its speed and location. If every location in the country had an auto risk value, then you can essentially match the car's location to the geographic location to determine the real-time risk. As the car passes from, say, the suburbs to the city, the risk will continue to rise, and so should the premium, as the drive happens. This way, both insurance company and the customers have a fair deal. The premium for any object is simply proportional to the risk, which in turn is a function of the cost of the object, the controller, in this case it happens to be the driver of that object, and the location. So how do we find these? Let's go back to the car. The cost of the car is well known, so no problem there. Insurance companies already have a lot of information on their customers. Information like their age, address, number of accidents, severity of such accidents, etc. The risk component based on the person does not change from instant to instant. So one can assume that the risk gradually reduces as the driver, say, matures and learns more. Accident, theft, catastrophic data for all the areas of the country is available, partially with the insurance company themselves, and partially with the federal and state organizations. Combining all this data, it's possible to construct a risk contour as the car's location changes using machine learning algorithms. The great thing about machine learning is that the more data you feed it, the more accurate it'll be over time. It can also adjust to long-term trends, ignoring small local variations. Insurance company that can get to this kind of a near real-time risk calculation will also have a huge competitive advantage because the earlier they get into the game, the more time they will have to fine-tune their models to get a more accurate premium calculation. So at some point in the future, your premium can actually be proportional to your risk. Thanks for listening.
Now that we've explored some business applications of data science, let's take a closer look at how data science is used to add value to business problems. To do that, we'll come back to our trusty Venn diagram. Recall that data science is the marriage of business acumen, statistics, and coding. One manifestation of that value is in the form of data processing and visualization. This includes getting the data, cleaning the data, and preparing it for data science. And not to mention the value that comes with presenting that data through intuitive visualizations and reports that the business can understand. Gaining a deep understanding of the data is a must for any data science project. The simple process of exploring the data can yield tremendous value to the business, so this step should never be skipped. Next up is research studies. This is where statistical expertise comes in very handy. In this domain, a trained statistician can analyze and make meaningful conclusions from the data, backed by rigorous statistical methods. This is where the correlation is not causation concept comes into play. This is also the domain of A/B testing and research, which both require deep formal training in statistics to be conducted properly. And last, but definitely not least, is machine learning, where statistics and coding come together to create algorithms that allow machines to pick up patterns in data that we mere humans could never accomplish due to the sheer size and complexity of the information. With that full picture in mind, let's zoom in on A/B testing, a popular method used by data scientists to evaluate a potential change in the business. In short, A/B tests, also known as bucket tests, are controlled experiments that use statistics to compare two variations. Common applications include website design, marketing campaigns, and medical studies. If done correctly, A/B testing can be a very powerful tool in helping a business make tough decisions. But before we dive into the details, let's lean on the following video to introduce the topic.
Your website is doing well, attracting hundreds, maybe even thousands of visitors and guiding them through their customer journey. That's great. But the beauty of a website is that there's always room for improvement, optimization, and growth. But knowing where to optimize is not so easy. Your social media expert wants you to cover your homepage in social widgets. Your sales team insists you need more product showcases linking directly to the shopping cart, while your graphic designer frowns at both and pushes you towards a cleaner, more minimalistic design. Who's right? None of them. The true expert in deciding how to optimize your website for greater success and business growth? Your website visitors. And to get a clear idea of what they love best, you need A/B testing. A/B testing allows you to question your long-held assumptions and put real data into results-driven action. So let's see how A/B testing works. Let's say you're running for president. You want to ensure that you're making the best impact you can with your campaign homepage, which currently displays your party logo, your campaign tagline, and a simple email subscription form. Here it is. Could do better. Perhaps a different image would work. What about one to demonstrate your lifelong passion for space? One that shows you're not afraid to get your hands dirty? Or a slightly adulterated photo of your last trip to Mars? What would your website visitors like best? Ask them. Using A/B testing, you can now split the 4 variants across your visitors and compare the results of each. Clear Analytics help you to see which variant wins in terms of conversion rate, and you can swap over to that version with one click. Having already dramatically increased conversion rates, you can, of course, further optimize the winning page by testing individual elements on it, like the heading, call to action, layout, subscription form, etc. And with so many more subscribers, you'll want to test your campaign newsletters and emails to ensure you're optimizing all channels. Because more subscribers means more supporters, and more supporters means more donations, and more donations mean, well, a majority vote.
Let's say that we also want to conduct an A/B test on our website for data science at Unify. Here's our current website, but let's say I want to try to drive an increase in email inquiries from the website by adding a video to the front page. To test the effectiveness of this change, I will randomly assign 50% of users to see page A and the other 50% of users to see page B. I'll then collect metrics to calculate my KPI of interest, the total number of emails I get per day for each channel. What I'm really doing here is testing the following hypothesis, and that is, adding video will increase the daily number of email inquiries about data science at Unify. And as an A/B experimenter, my goal is to determine if there will be enough evidence at the end of this experiment to accept or reject this hypothesis. So let's say this is the distribution of my A users. On some days, I only get 1 email per day. On other days, I get 10 emails per day. Good days. But on average, I get around 5 emails per day. Now let's take a look at our B audience. If I were to ask, is this a significant enough increase? What would you say? It's kind of hard to tell. The increase is so small, it's difficult to say confidently that the video sustainably increased the number of emails per day. If we were to run this experiment again, B might be lower than A. It's too close to call. But what if the B audience had this distribution? Now things are looking a little better. I would argue that the B test was successful compared to the A test in increasing the number of emails per day. But this eyeball test is not exactly the most rigorous method for determining the success of my A/B test. Fortunately for us, there is a widely accepted method to determine whether or not a change in distribution is significant or meaningful. And that test is called the t-test. Let's do a quick overview of how to measure the t-test statistic. In simple terms, this calculation yields a number that tells you how unlikely something is. The bigger the number from the t statistic, the more unlikely it is for something to happen due to random chance. A good analogy is to think about dice. Let's say you're playing Monopoly, but your opponent rolls a 12 or 2 6s on 5 consecutive rolls. Now you're probably thinking that's incredibly unlikely. You know from experience that the chance of rolling 12 5 times in a row is almost nil. So you make an alternate hypothesis in the back of your mind that your opponent is cheating using weighted dice. Well, you just effectively ran a mental t-test. Now once you've calculated the t-statistic, the next step is to convert that number into a probability. That probability is called the famous p-value. The p-value is infamous for being confusing and misleading, so let's take a moment to define it precisely here. Assuming that the null hypothesis is true, the p-value is the probability of observing an outcome, or an even more extreme outcome, based on random chance alone. That's a mouthful, so let's go back to our Monopoly example to make it a little more visceral. Well, it turns out that the probability of rolling 5 12s in a row is practically 0. So the p-value is also 0. So assuming that our null hypothesis, that the dice are fair, is true, it's pretty much impossible to roll 5 12s in a row. So given that your opponent actually did that, it's fair to reject the null hypothesis that the dice are fair and accept the alternate hypothesis that the dice are weighted. But how low does the probability have to be before you can conclude that your opponent is cheating? We know from the previous example that the probability of rolling 5 consecutive 12s is nearly 0, so it's pretty easy to reject the null hypothesis that the dice was fair. But what if the probability had been a little higher? What if the probability was only 2%? Still pretty low, but unlikely. What if it was a 5% chance? Again, also pretty unlikely. Well, where do you draw the line? In statistics, the drawing of that line is called the alpha. Generally, a rule of thumb is to set alpha to 5%. If the calculated p-value is less than alpha, then you can conclude that the test is statistically significant, which means you can formally reject the null hypothesis. In our example, our null hypothesis was that a video would not improve email volume. And let's say we had set our alpha to 5%, and our experiment yielded a p-value of 2%. Well, in that case, we can conclude that the video does improve email traffic. In other words, a successful A/B test. Okay, that was a lot of statistics lingo, so let's break it down to simple terms once more. A friendlier definition of the t-test. If your experiment yields an outcome that is very unlikely to happen by chance, then it's a good bet that your experiment worked, and you can make the change that you're looking to explore. All right, on to machine learning. This buzzword has dominated the narrative in the data industry for the past few years, with every major publication providing coverage of machine learning ad nauseum. But it's not all hype. It's a technology that has driven some of the most amazing advances in applications and devices today. Machine learning is behind the facial recognition and object detection technology in Amazon Go's checkout-free shopping experience. It's behind the camera technology that powers self-driving cars. And machine learning's ability to comprehend human language is also the reason why home voice assistants have become so prevalent today. Understanding machine learning is a critical component to our aspiration for AI leadership, so let's take a moment to demystify what it is. The big idea is this. Machine learning is a field of computer science that uses statistical techniques to give computer systems the ability to learn how to perform a task using data. And this is done without being explicitly programmed. What this means is you don't have to program each and every step to enable a computer to learn something. Instead, you provide a learning algorithm and let the computer learn how to do something on its own. Let's see what this looks like from a high level. In machine learning, you start off with data that's been cleaned and prepped for machine learning. That data is then fed into a learning algorithm, which finds patterns in the data, many of which are incredibly complex and extremely difficult, if not impossible, for humans to find. After the algorithm crunches the billions of rows of data through a process called training, it saves the patterns it's learned into something called a machine learning model. This model is one of the key deliverables in a machine learning project. Once the model has been vetted and tested for performance, it can then be used to make predictions on new data. So this process is repeated over and over again, allowing the machine learning model to become smarter and more accurate over time. So from this vantage point, machine learning is actually not that different from human learning. It's actually quite intuitive. That simple process has led to an explosion in useful machine learning applications. In fact, the adoption of machine learning in both industry breadth and task depth has been nothing short of amazing. Let's zoom in further to understand what types of tasks machine learning is well suited to do. Generally speaking, there are three types of tasks that machine learning does well. One is regression. When you see regression, think of predicting a number, such as a stock price or the weather temperature. A second type of task is called classification. With classification, think A or B, a dog or cat, a customer or a churned customer. And the third task is called clustering. In clustering, machine learning groups together like things, such as a group of documents, or a group of tweets, or maybe a group of pictures that all have something in common. Any given task can be performed by a machine learning model, but only after it has been trained on relevant data using any one or combination of algorithms. Okay, so which algorithm should I choose? That's where the data scientist's expertise comes into play. Certain algorithms will perform better than others in speed, while others will outperform in accuracy. It's up to the data scientist to understand the trade-off between the two and work with the business to understand the best balance. To make this more concrete, let's walk through an example of applying a decision tree algorithm to create our first ever machine learning model.
Let's get our hands dirty and dive into an example using decision trees. Now let's say you've been tasked with determining whether or not a home, based on the data alone, is located in San Francisco or New York, two very pricey markets. Well, you know that San Francisco is very hilly, so maybe you bring in some elevation data and use that as a way to split the data between New York and San Francisco. As you can see in this visualization, that seems to be a pretty good place to start. In fact, any home above 239.5 feet of elevation is a San Francisco home. But you're an enterprising data scientist and you want to do better, so you bring in a little more data, maybe a second dimension, for price per square foot, and you put those on an XY scatter plot. Aha! Now there's another cut you can make to further separate the data. Recall that we already made one slice at 239.5 feet of elevation to separate the San Francisco and New York data, as shown in the green area above. Well, looking at this two-dimensional scatter plot, you can also see that you can make a slice at $1,776 per square foot to make another clean split in the data, as shown in the blue area here. You now realize that this is an effective way to look at various relationships between data and find more places where you can slice the data cleanly. Here's a series of scatter plots showing various relationships between the data that you have. Now, it's not immediately obvious where you can make more quick slices in the data, and you're probably thinking, that's a lot of charts I have to go through one at a time to find more manual cuts. So, you decide to use machine learning instead. You pass your data into a decision tree algorithm, and you let the computer do the heavy lifting at 1,000,000 times the speed. This process of giving the algorithm your data and letting it find these patterns is called training. Well, now that your model is trained on tens of thousands of rows of data, you want to test it. Let's see how accurate the model is using the same data that was used to train the model. Hey, look at that, 100% a perfect score. But is that really a good indicator of the model's performance? After all you did was give it the same data that it used to find the patterns. In other words, all it did was memorize the data. What were to happen if we were to give it new data that it's never seen before? How would it perform? Well, let's check. Here's some data that we pulled off from the shelf that the model has never seen. Interesting. It's no longer 100%, but rather a disappointing 89.7%. So what happened? What we just witnessed together here was the cardinal sin of machine learning called overfitting. Overfitting is the process of memorizing the data so well such that the model does not generalize to new unseen data. Here's a simple illustration of overfitting. The y-axis is the number of errors that a model made when making predictions. The x-axis represents the duration or the length of training. The more training you do on a given data set, the more accurate the model becomes on that data set. The blue line indicates the model's performance on the training data, while the red line indicates the model's performance on new, unseen test data. You can see that the blue line approaches 0 over time, and the red line bottoms out and then starts to get worse over time. This is called overfitting on the training set. This is very similar to the situation where you memorize the homework questions, but you don't develop an understanding of the underlying concepts. So when it comes test time and you encounter questions you've never seen before, you struggle and you get a lot of questions wrong. The ultimate goal of using machine learning is to create models that can predict the future accurately, not the past. And in this case, we want to train our model so that it stops at the minimum of the red line, not at the minimum of the blue line. The red line is a real test of your model's ability to predict the future. As you collect more data, you can further improve the model by training it on new observations. Just like a human being, a model also learns from experience and improves over time. So that's it. Machine learning seems like a big, scary thing, but it's really just these 5 steps applied to different business problems. As long as you have enough data, a good model, and you avoid overfitting, well, you can create artificial intelligence with the best of them.
So we've looked at machine learning, but now we're really going to look under the hood and look at algorithms. Formally defined, an algorithm is a process or set of rules to be followed in calculations, usually by a computer. In machine learning, what that really means is an algorithm is used to find useful patterns in data. Now, we talked about all the tasks we can do with machine learning, and we talked about different algorithms that can be applied to do those tasks. Well, it turns out depending on your business problem or what you're trying to achieve, any subset or combination of these algorithms can be used to do just that. Some algorithms do better than others in terms of performance, but some algorithms are easy to explain and understand. In fact, some algorithms are so complex that we human beings don't even know how they work. An example of that, neural networks, also known as deep learning. Now, deep learning has unlocked a whole new world of capabilities for machine learning, especially in the worlds of computer vision, natural language processing, and all the things that we consider as cognitive tasks. In fact, it's so important, we're going to watch a small video on what deep learning is.
Deep learning is a set of algorithms, combinations of math and code, that loosely resemble neurons in the human brain. Deep learning can achieve human-level accuracy on tasks like image recognition, voice recognition, and predictive analytics. It's basically machine perception. We have given machines eyes and ears and an intuition of the future. Deep neural networks map inputs to outputs. They find correlations between those two sets of data. Companies are applying deep learning for machine translation, speech-to-text, facial recognition, voice recognition, sentiment analysis, predictive maintenance, and healthcare. Deep learning performs 3 kinds of analysis: classification, clustering, and prediction. Classification could be putting names to faces or applying a spam filter to email. Clustering could be image search, uploading a product photo and finding similar products, or text clustering like uploading a legal document and finding related texts. Predictions could be using a stream of current data to anticipate the future based on an understanding of historical patterns. This can be applied to vital statistics in healthcare, or stock price action in securities, or market forecasts for national economies. That's it. Deep learning solves a lot of hard problems better than we've ever solved them before. It also provides a basis for new products and business lines, because it lowers the cost of thinking, unlocks value in data we're already collecting, and makes it possible for small teams of analysts to process much more data.
Neural networks, again, deep learning, are the future. The problem is they're really hard to do because number one, they need a lot of data. Number two, training is extremely slow because of the volume of data and the computational complexity. And number three, expertise is really hard to find. But it is the future, so it will serve us well to understand all the technologies behind deep learning and what we can do to bring that technology to clients.
All right, we are almost there. So hang with me just a little while longer, because the next point is critical. Up to now, we've reviewed a few algorithms together. We even walked through a decision tree algorithm in detail to help decide whether or not a property is in New York or San Francisco. But as we've talked about a couple times already, the decision of which algorithm to use is an important one. Sometimes the business problem is so complex that you have no choice but to use the most powerful and most complicated algorithms to achieve the desired performance. And this often leads to the black box problem. A black box model is a model that's so complex that the business has no idea how it works. This is really problematic in regulated industries such as finance. Regulators often want to know, how is the machine learning model making a decision? Is it being fair? Is it being discriminatory? What factors is it taking into account? Some algorithms are so obscure that it's impossible to answer those questions. Sometimes the black box problem is less about regulation and more about comfort. Think of it this way. Let's say you order an Uber, and up to the curb pulls a self-driving car. A self-driving car that you've never seen before, you've never heard of, and you certainly don't understand how it works. Would you just hop in and take it for a ride? Probably not. You would pause, ask yourself a few questions, see if you can confirm how the camera works, how the braking works, and ultimately whether or not the car can get you to your destination safely. Machine learning works the same way. When a client comes to us and asks for help on a business problem using machine learning, they're entrusting us to provide something they can believe in, that can stand behind. A critical part of achieving that level of confidence is building the trust. The trust in you as a data scientist, the trust in you as a partner, and ultimately, the trust in what you deliver.
All right, so we're going to wrap it up here, but let's do a quick review of everything we've covered. We looked at some really interesting use cases that happen in industry. We broke it down into what data science really means in terms of the Venn diagram. We looked at some examples in A/B testing and in machine learning, and we even talked about algorithms, which is pretty nerdy. And that's a wrap. That was Introduction to Data Science for Unifi. My name's John Kim. Thanks for listening.